Okay, in this video we're going to do some more examples and learn more about using pointers. In particular, we're going to use the dereferenced pointer, which means the thing that the pointer is pointing to do some arithmetic operations. We're going to learn about pointers in two-dimensional arrays and using a pointer with functions. So moving on. So before I do that, let's go back and review a little bit what we did last week. With another example. So this is a one-dimensional array, and this time I made it a one-dimensional array of long ints. So notice how I declare my one-dimensional array of long ints. And the reason I declared it long is just because I'm showing you memory usage, because a long int takes a certain number of bytes and an int takes a certain number of bytes. So I'm just showing you some different things. So I've declared this array of long ints, and this is how I declare longs. And then I made a pointer to my array. My array name is multiple. So I made a pointer p to multiple. And then I'm just going to look at what some values are down here and some addresses just to refresh what the dereferencer asterisk means and what the ampersand, which is a address operator, means. So I just have a for loop that's going to print out some information as it goes through this array. This array right here, I have it shown over here. The values are 15, 25, 35, and 45, the values stored, and they're stored at some address, and my little piece of code down here tells me what address that they're stored in. And I didn't show it in hexadecimal, I showed it in numbers that long unsigned ints, so I could see the whole address. But I have it in base 10 so that we can count up easier, because most people don't count up in hexadecimal very well, but we count up in our base 10 numbering system just fine. Okay, so here's my for loop, and it's for I equals 0 to some maximum value, but my test of when the for loop ends, I said I less than, and I have the use of size of function here. So size of multiple will say how many bytes the whole multiple array takes up, and then size of multiple element 0. Let me get my pen here. Oh, pen's not coming up today for some reason. Okay, my pen isn't working. Okay, I can't mark. Okay, so I'll just have to use my cursor here. But size of multiple element 0 would be the size of how many bytes this value takes up. And so how many bytes does a long int take up is the question. So maybe my array takes up, it actually takes up, I could see it down here in the addressing, 8, 16, 24. It takes up 24 bytes, and actually takes up 24 addresses. So we'll figure that out here in a moment. So the size of one element in bytes divided by, or the size of the whole array in bytes divided by the size of one element in bytes, and that tells you, it should give you how many elements there are. So it should be 4 elements in the end. And so here's my sort of cryptic printf statement, keeping in mind that unless I have a percent sign, I'm printing literally. So I'm saying the address of the pointer, and plus this iterator here in a moment, which is I. So I is going in here. So my I is 0, 1, 2, 3. 0, 1, 2, and 3 is the values of I that go in here. So the address of the pointer plus, and I don't give the, it's literally text that's coming out here, and you can see, plus my iterator 0, 1, 2, 3. So the first line should give you the address of p plus 0, and which is the same as the address. So there's my address operator, the ampersand right there, the address of multiplier element 0, because it's 0 the first time we go through that. And then it is right here, I'm outputting actually the unsigned long pointer value. What is the the pointer address, the thing stored in P. So the thing stored in P is an address right here. The thing stored in P is an address. And unless I put a star in front of it, the dereferencer, if I put the dereference in it, then I will get the value that it's pointed to. So that's what this somewhat hard to read, you should get used to reading nomenclature means. And then I have one last statement here that the type long occupies how many bytes. So here's the output that I get. So the address that is held at P initially, so the address held at P is the same as the address of multiple element 0, and that is the address right there. And then the value of dereferenced P is 15. So the next address of pointer plus 1 is the same address as multiple element 1 is, and it's this address, and you can see that it's 8 bytes later. So even though I'm saying pointer plus 1, it knows how big of a thing is stored in the array, and so it increments this address stored at pointer. So this is the address stored at pointer. It increments it appropriately. It increments it by 8 bytes. So pointer plus 1 is this address, and sure enough it says that. Pointer plus 2 is this address, and the value there as dereferenced by this asterisk is 35. And pointer plus 3 then this address will hold, the value of P will hold this address then, pointer plus 3, and if I dereference it, the value will be 45. So that's a nice little review, and I don't have the last printf statement on there, so I can go ahead and I think I have it up here. Yeah, here it is. So type long occupies 8 bytes, and surely that's what we see when we run the program. Okay, let's do another example, and let's start talking about 2D arrays now. So here's a 2D array. So I've declared a 2D array. I actually call it the array board because this is a little piece of a program that will program a tic-tac-toe game, which I think we are going to work towards. But initially you define a tic-tac-toe board, which should be a 3x3 matrix of some kind, but I'm giving it character to identify each location in the array. So it's just an array, a 3x3 array holding characters 1 through 9, and my array is called board. And then I have a little piece of code down here that prints the address of board. So I'm going to get, why am I going to get an address when I do this? Because I said that the format specifier right here is a %p, which will give me a pointer address. Notice I haven't even declared any pointers in here. And then the address of board element 00 is, and I ask for address of board element 00 right here. Then I have print the value of board element 0. Well, what do I mean by board element 0? So that's what I'm going to talk about in a minute. And then I say print the address of board element 0. So let's see what happens on this program. So I ran the program, and you may be surprised, or maybe not, but you see these are all hexadecimal addresses. So address of the board array is right there, which is the starting address of that array. Address of board element 00, well, as you expect, it's the first address of where the array is located. And then address of board element 0, it again gives you the same address. So one thing about 2D arrays, I'm going to go ahead and I went ahead and pasted this in here, is that it's not, you don't have a 2D structure in memory. So what you have is an array of 1D arrays to make a 2D array. So literally in memory, and these would be, I would put addresses out here if I should have put the addresses out. We could have. We'll do that in the next program. But you can see that 1 is in the first address, 2 is in the second address, and however many bytes is put aside depends on what the declaration here is. I believe character is only 8 bytes, so I'll be going up I believe a character is only 1 byte, 8 bits, so we should only be going up by 1 byte at a time in addressing. But you can see the first row is here, the second row is here, and the third row is here. But in addressing, they're really sequentially addressed. So let's play with this example a little bit more. So now I have still the same board array, 2D array declared, and I'm saying to look at the value of board element 0, 0. Well, you guys are pretty good at that right now. That would be obvious. It's going to be a number 1, right? And then the value of, and look at my use of the dereferencer here. So we'll see what that results in. So I have a single pointer, a single dereferencer to board element 0. And then I have this dereferencer used twice here. So the question is, what happens? Oops, wrong one. So just slide. So when I print these values, it's sort of what you expected because everybody points to a 1, but these are not the same things. So even though the answer is always 1, what I'm actually asking for is different. And let me explain the use of the double dereferencer here. So the 2D array is notionally an array of 1D arrays. So when you declare the two-dimensional array, you're creating really an array of subarrays. And you can access the whole array and the address of where the whole array is using the array name and a single index value. For example, I have it shown right there, right? So that will reference the whole array right there if you do that. It also addresses the beginning of a subarray that's at 0. So here were 3 different expressions that we saw in the program, and they all resulted in the same addresses back here, these addresses, right? They all resulted in being in the same address, but they have different meanings. So, for example, board is the address of a 2-dimensional array of character elements. Board 0 is the address of a 1-dimensional array of character elements that is a subarray of board. So, for example, board 1 would be 4, 5, and 6. Board 2 would be 7, 8, and 9. And then if you say specifically with the address operator ampersand board 0, 0, it's the address of one particular element in the array. So even though these are giving the same addresses, they are not the same thing. So let me run that example a little bit different to show it to you. I changed this program a little bit. It's still the same character array. I have the address of board. Generically like that should be the address of where the board array starts. Address of board element 0, 0. Oops, let's make that 0, 1. Oops, yeah, 0. I compiled it wrong. 1, 0, and then I'm going to ask for the address of element 1, 0, and then I'm going to ask for the value of board 1. So this address, board 1, is the address of the beginning of that subarray, the first subarray, row 1, basically. So we have row 0 and row 1 and row 2. So this should be the address of row 1, and it should match the address of the first element in that array. So that's what should happen. And let's compile it and see. So here it is down here, at the bottom of my screen. Actually, let's clear it and make it easy to see. So the address of the board array is here. The address of the first subarray is three addresses later on, because I used up 1, 2, 3 bytes, 0, 1, and 2 here, and this is byte 3, 4, and 5 will start here, or the subarray 1, row 1. And then, so that's the first element in it. And the value of board 1, which is the first subarray, or the row with subscript 1, because we have row 0, row 1, and row 2. So row 1 has this address, which is the same as the first element in that subarray, which is 3 bytes away from the beginning of that array right here. And I will just show you that it's 3 bytes away. One more quick example. So what if I wanted element 1, 1 here? So that should be 1, 2, 3. That should be, should tell you what the value is here too. Compile it one more time. So yes, I've upped the address by 1 because I have element 1, 1, and you know which one is element 1, 1. Element 1, 1 is a 5. So, okay, good. Let's go on to our next example. So now I'm going to do one of the some of the examples in your textbook because I think it helps make things clearer. So this is the practice problem on page, I think it's on page 302, 301. So, and the answer is in the back of the textbook, but then there wasn't really good examples in there. So we'll go ahead and do it and talk about it. Grab my pen. My pen is working now. I just reset my computer and then it started working. Amazing how that works. Okay, so it says draw the memory allocation for each of the following arrays and indicate the values stored in those locations. And then put a question mark if it's not assigned. So also indicate offset from the initial array value for each of the array elements. And the reason we have an offset is because we're not given exactly where that's stored in memory. So number 1, we're declaring an array, and it's a 4 by 2 array. So literally number 1 would mean that it's something that has 1, 2, 3. It would have 1, 2, 3, 4 rows, and then 2 elements. Got to work on drawing straighter. But that's not how it's stored in memory, of course. In memory, it's stored sequentially. So, so this 4 by 2 array would have 8 elements in it. So it's going to take 8 locations in memory. See if I can get this to draw straight. No, straight. Okay, I'm straighter now. All right, sorry. So how would it look in memory? So in memory, we'd have D element 0, 0, and then D element 0, 1, D element 0, 2, and no, we wouldn't have 2. Why? Because it's four rows and 2 columns. So our 2 columns are D element 0 and D element 1, or column 1. And then we'd have D1 element 0, D1, 1. And then we have D2 element 0, and then we have D2 element 1. So I need 4 rows. So I would have the 4th row, which is subscript 3, 0. So these are all of the individual elements in the array, but what's in these memory locations is the question. Well, so I made a declaration for this array, but I've only given the first value. And of course we have to have double curly brackets because it's a 2D array. So the first memory location contains a 1, and the second memory location contains a 6. And then the rest of the array just gets filled with zeros. So the offset that the book is talking about, offset, is because I have an initial address right here. So that's my 0 starting point. The next address that a pointer would point to is here. Even if these numbers take several bytes to contain them, the next address that a pointer would point to in an array is here. So that's the first address offset. It's really an address offset. Second, third, fourth, fifth, sixth, seventh. So I would take up 8 locations in memory, and it would be ordered sequentially like this, with the first address being here, and also the address for that array. So number 2. Number 2 is a 3 by 4 matrix. So that means it has, I'll draw it a little differently than my horrible looking thing right there. So that means it has 3 rows, but 4 columns. So it's something like, I'll just draw it in like this way. This is a 4 by 3. So 3 rows, 4 columns. This is element 0, 0. This is element 0, 1. 0, 2, 0, 3, and this would be 1, 0, and this would be 2, 0, etc. So that's the array itself, but how does it go in memory? Let's show the memory allocation for it. So this array is called G. It's 3 by 4, so there's going to be 12 elements. So this is where the first element resides, and it's going to do it in this order. This is the first subarray. So this is the first subarray. So if I referenced G0, I would be pointing to that first subarray. Second or subarray would be also with 4 elements in the subarray. And then we number again, 0, 1, 2, 3. Hope you're getting the idea now. How far do I need to continue? I'll continue over here in the next column. So G2, this is the third row now happening, and it has 4 elements in it also. Third row, or third subarray. 1, 2, and so that's my 12 elements. This is the first subarray, this is the second subarray, and this is the third subarray. So if I referenced, for example, G1 without saying, whatever the address is at G1, I would be referencing this address right here, which is the start of this subarray. So again, this one started off by giving you some of the values, but it will be filled in sequentially. So we will have a 5, 2, -2, 3, and then this is the second subarray, first subarray, second subarray, 1, 2, 3, 4, and these values will not were not given, so they would end up being a 0, 0, 0, 0. They would be filled in with zeros. So the offset, the address offset, this is the starting address, so address plus 0, address plus 1, 2, 3, so kind of trivial. This is offset 7, 8, 9, 10, 11. So if I were to point to this single element here, it would be at the starting address plus 11. So, all right, one more. I think I'll go ahead and erase that so I can put my one more example on here. One more example we need. Oops. Oh, I'm having trouble erasing. Okay. Okay, last example, number 4. This is a float, so really the question is how big of a memory element, how big of a memory location would float use? But it's an H. It doesn't really change anything. It's a 3 by 3, so 3 by 3 is 3 rows, 3 columns, like so. This is 0, 0, 1, 0, 1, 1. And this is 0, 1, 0, 2. This is 1, 1, 1, 2. This is, oops, 2, 2, 0. 2, 1, and 2, 2. So that's how it would be if we look at it considering ourselves, our humans, and thinking it's a 2D array, but memory is not really 2D, so it's going to be stored as an array of subarrays. Oops. There's the first subarray. Here's the second subarray. And the elements of it. And here's the third subarray. And each of the elements in that subarray. And so what's stored there? It just says zeros. So the whole thing, this one will put a 0 in that spot, but everybody else will get initialized by zeros also. So 0 in everything in that array. Not too exciting of an array. This next example is an example of using pointer arithmetic. Well, part of it is. So assume that an integer array x is defined by the following statements. So I create an array x, and I create a pointer to the first address of the array right here. So a pointer to element 0, 0. It says draw the memory allocation diagram and give the value indicated by each of the references. So notice each one of these examples is using the dereferencer, which means it's pointing to the value that's stored at that location. And where x pointer holds the address, star x pointer points to the value that's stored at that address. So the first thing I would do is write out what x is. X is a 2 by 4, so it's got 2 rows, but it's got four columns, 4 elements in the column. And it looks like they completely defined this array. So in memory, it would be stored as, so this is 0, 0, 0, 3, and this is 1, 0, 1, 3 over here element. Okay, so x 0, 0. This is the way you would reference any of the individual elements in this array. One, 2, 3, and 1. So that would access any individual element in the array, but in memory, this is at the first memory location, and right here is our first subarray, and here's our second subarray. So it says, and that's what's in these memory locations. So it's 1, 8, 7, 6. Second subarray right here, 2, 4, -1, and 0. And what's the offset? This is first address plus 0, first address plus 1. Where the address must consider the size of the variable that's stored there. Oops, 6, 7. So that's offset. And that's the value stored there. Okay, so it says what's the value pointed to by, and we've declared that the value of that the pointer is going to point to the first address of this guy, address right here, which is at offset 0, 0. So maybe the address is something like 0x43DD70 or whatever the address is, but that's the starting address. So starting address plus 0 is right here. So this is pointing to, because I'm using the dereferencer, is pointing to what's stored at that address. So problem number 1, it's what's stored there, and it's a 1. Problem number 2, what's stored at the address of the pointer plus 2? So it's 0, there's plus 1 and there's plus 2. So the value stored there is a 7. The value of this expression is 7. Number 3, now I'm going to say the value that's stored at the 0th location plus 2. So the value that's stored there is a 1, but I'm adding a 2 to it. So the answer is a 3. And number 4 says the value of the address that x pointer points to plus 1, so this is what's pointed to plus 1, which is this guy right here, plus the value of the thing that's at 3, the address plus 3, so 1, 2, 3, it's this one, and the answer is 14. So the next example, I'm actually refreshing you on doing a function with pointers. We actually looked at this switch function, I think we called it swap function, in last week's YouTubes, but let's look at it one more time, just to refresh your memory about functions, because you have a homework problem where you're going to have to do a function with a pointer as an argument. So I've declared this function right here. This is just a function. Assuming we assume that we have somewhere else a main body of the program that's not shown. And the arguments to this function are pointers. So when I pass values into the function, I'm going to be changing things that are at memory locations pointed to by these pointers. And let's see, actually I did that in the, I'll refresh your memory on that slide that I did in the last YouTube. Here is the one, I called it swap last time, and I have shown with a true function call. So here's a pointer that points to the contents of an address right here. So it's not pointing to an address, but pointing to a contents of an address. And then when we call this function, we have to pass in an address. So address of C and address of D gets passed in this case and does the swap. So this was the example I did for you last week, but back to the example that's actually in the textbook here. They gave a few other examples. This is very similar. Is that one way to call this function is by passing address of a variable x and address of a variable y, and that's okay. It's expecting to have the contents that are being pointed to by an address right here. Another way, assuming that these are pointers with addresses, is you could pass in that to the function call. And you could also pass in address from an array, address of a certain element of the array, and address of a certain other element in the array. That's okay too. And this function call right here, assuming x is an array, if x is an array right here, this is also a valid way to call this function. So you are looking at an address of where the array begins plus an offset right here. So this is an address plus an offset, and this is an address where the array x begins, and this is an offset. Invalid is passing to just values like element I and element j of an array. This would be an invalid statement. So you must pass addresses into this function, or pointers to addresses is all right too. So with that in mind, this program that we just looked at again, let's take a look at the one last practice problem here that for this chapter that we're going to go over, and see if we can see if our calls to this function are valid calls or not valid calls. And if they're not valid calls, what are the reasons that they aren't valid calls? Okay, so the first example, I declare floats x and y, and I declare pointers to the addresses of x and y, and then I call the switch function. And this one was a little bit tricky because this one is actually invalid because of a mismatched data type. So let's look back here at the function. Everything has to be an int here. We're swapping ints. And for that matter, the example I did last week, everything was a character. in the swap. So we were swapping characters. This time we're swapping integers. So this one is, so the first example here is not valid because of these wrong data types. So now let's look at the second one here. So I'm declaring integers this time, and pointers to the address of f and pointers to the address of g, and then I call the switch function right here. And I said that this one was valid, and then I looked back in the textbook, and your textbook solution says it was not valid for, what was their reason they gave? Oh no, this one is valid. So this one is valid. I actually programmed it just to check it in my swap function, and then it was definitely valid. So these are actual addresses that, this is an address that is being given right here. Not the pointer to the value, but the actual address. So number 3, I have the same int declaration and I have the same pointer declaration, and this time I call the switch function with the dereferencer in there. So that says I'm actually pointing to 7. I'm passing 7 in and 2 in, and not pointers. So it's not valid because I'm not passing a pointer or an address. I'm not passing address or pointer to an address. So this one's not valid. Not. Number 4, so I have the same integer declarations, the same pointer declarations, and I'm asking for it to pass in the address of pointer f and the address of pointer g. That's not valid. That has to not be valid. Oops, this one. Right, not valid. Not valid because I'm passing in the address of the pointer, not the contents of the pointer. The contents of the pointer are the addresses of f and g. So these aren't addresses to f and g here. These are addresses of the pointer itself. So not valid. Number 5, looks like it's the same variable declarations up at the top. And it says call the switch function with the address of f and the address of g. So that's valid. Okay, and number 6, looks like I have the same declarations here. This is not valid. Not valid because these are values of f and g here. They are not addresses or pointers to addresses.